All right, let's talk about a really powerful idea called dynamic programming. It's kind of the secret sauce behind teaching a machine how to come up with the absolute perfect plan. Whether it's winning a game of chess or running a massive global supply chain. So let's dive in.
I mean, really think about that for a second. Anytime you're planning something, a trip, a project, anything, you're facing this long chain of choices. And every single decision you make opens up some new possibilities, but closes off others. So the big question is, how do you find that one single path that guarantees the best possible outcome at the very end?
And trust me, this is way, way harder than it sounds. A chess master is thinking dozens of moves into the future, knowing that just one wrong step can lead to a total disaster down the line. And it's the same for an AI managing a supply chain. A single choice can have ripple effects for months. What they both need is what's called an optimal policy, a perfect, forward-looking plan.
And that's exactly where dynamic programming, or DP for short, comes in. It's this brilliant method for solving these huge, messy planning puzzles by just breaking them down into smaller, much easier to solve pieces. But there's one catch. DP only works its magic when you have a perfect model of the world. You have to know all the rules of the game right from the start.
Okay, to make this whole thing feel really intuitive, we're going to use a simple analogy for the rest of this explainer, planning the absolute perfect day at a theme park.
So your goal is super simple. Have the most fun you possibly can before the park closes. And you've got everything you need, a map that tells you how long it takes to get from one ride to another, and you even know the fun score for every single ride. This map, this is your perfect model of the environment.
So let's quickly translate this theme park idea into the language of AI. Your state, that's just where you are right now, like at the roller coaster. An action is just your next move, walk to the Ferris wheel. Your policy, that's your entire plan, your whole route for the day. And the value? Now this one is super important. That's the maximum possible fun you can have starting from any spot in the park.
So that map you have, it's basically a cheat sheet, kind of like this table. It tells you everything. If you're at the entrance and you decide to go to the roller coaster, it's going to cost you 5 minutes, and you get a reward of plus 50 fun points. See? Dynamic programming needs this complete rulebook to do its thing.
So, how does DP actually use this map to find the best plan? Well, it's this brilliant two-step process. First things first, we need a way to figure out how good any plan really is. And that means we have to calculate a fun score for every single location in the park.
This is the key question we have to answer. What's the value of being at the roller coaster? And it's not just the fun of the ride itself, right? It's all the potential fun you could have for the rest of the day, starting from that exact spot.
Now, in reinforcement learning, this is called the value function. But for our analogy, we're just going to call it the fun score. Think of it this way. Every spot in the park gets its own score that represents its long-term potential for fun.
And how do we actually calculate that score? Well, the logic is really beautiful. The fun score of being at the roller coaster is the fun you get from that ride right now, plus the score of the next best place you can possibly go from there. This simple but powerful idea is really the heart of the famous Bellman equation.
The way we find these scores is by going over them again and again. We start with total random guesses. Let's just say every location has a fun score of 0 to start. Then we just sweep through the park over and over again. Each time we visit a location, we update its score based on the scores of its neighbors. And we just keep doing this until the numbers stop changing. At that point, we know they've settled on their true values.
Okay, so now we have our fun scores for every single location, all based on our initial, probably pretty random plan. This brings us to the second and really crucial step, using those scores to make our plan way, way better.
And this is the improvement step. So instead of following our old random plan, where maybe we just flip a coin to decide where to go next, we create a new, much smarter one. Now, at every single location, you just look at your map and walk towards the next spot that has the highest fun score. It's a simple, greedy approach, and it's guaranteed to be an improvement.
So now, let's connect these two pieces, evaluation and improvement. Let's see how they fit together to create this powerful engine that finds the perfect plan.
The whole thing really just boils down to a simple, elegant loop. You start with any random plan you want. First, you evaluate it. You calculate the fun scores for every spot. Second, you improve it by creating that new plan that just follows the highest scores. And then you just repeat. You evaluate the new plan, you get new scores, and you improve it again.
You just keep running this little two-step dance of evaluation and improvement. And here's the amazing part. Eventually, the plan is going to stop changing. And at that exact moment, this process guarantees, mathematically guarantees, that you have found the single best, provably optimal itinerary for your day at the park. No more guesswork.
But this all brings us to the final, and I think most important question. What makes this whole thing so much better than just, trying out every single possible route one by one? The number of possible routes through a theme park, or moves in a game of chess, it's astronomically huge. You could never ever check all of them. So what's the secret here? What's the magic behind DP's efficiency?
And here it is, the secret sauce. Dynamic programming is efficient because it's smart and also a little bit lazy. It solves a small problem, like what's the best path from the Ferris wheel? It solves that just one time. Then it stores that answer and never has to calculate it ever again. By remembering the solutions to all these little pieces of the puzzle, it avoids redoing a ton of work.
So if you remember just one thing from all this, make it this. Dynamic programming finds the perfect master plan, not by looking from the start, but by first finding the perfect mini-plan from every single possible point on the map. It teaches us that to solve the biggest puzzles, you have to start by understanding the value of every single piece.